Hi, I'm Siddhant Arora and I'm going to give a presentation on AVL Trees. This presentation has been jointly created by me, Siddhant Arora, and my group partner Ankesh Gupta. Now in this current slide, we talk about the contents of our presentation. First, we will give an introduction to binary search trees and why there is a need for binary search trees. Then we will give an introduction about AVL trees. Then finally, we will discuss about insertion in an AVL tree. Now, binary search trees are trees in which all the nodes in the left subtree to a node have value less than that node, and all the nodes in the right subtree to a node have value greater than that node. All the binary search tree operations are of the order of order depth, where D is the tree depth. We assume that you have some basic knowledge about binary search tree before watching this video, and hence we have written here intuitively that all binary search trees operations are of order D, where D is tree depth. Now the minimum depth is given by D equal to log n for a binary search tree with n nodes. This is the case where for a best case binary search tree where each non-leaf node has exactly 2 children. However, there can also be a worst case binary search tree where each non-leaf node has only 1 children. Best case running time of binary search operation will be given by the minimum depth for binary search tree, which is order log n. Now we will do a binary search tree worst case analysis. We'll see that the worst case running time is of the order of n. This happens when we insert elements into a binary search tree in a sorted order. For example, when we insert elements in ascending order, that is 2, 4, 6, 8, 10, 12 into an empty binary search tree, then it will create in a worst case binary search tree. The problem in a worst case binary search tree is that there will be a lack of balance, that is, one of the subtrees will have a height of order n, whereas the other subtree will have height of -1. The unbalanced days worst case binary search trees are known as unbalanced degenerate trees. Here we are giving example of balanced and unbalanced binary search trees. Here the binary search trees in the top right and bottom left are balanced binary search trees, whereas the binary search tree in the middle is an example of unbalanced binary search tree. Now, in this slide, we talk about approaches to balancing trees. We can have various approaches towards balancing trees. One of the approaches is that we don't balance a balancing tree. This means that we simply add. We say don't rearrange the nodes during insertion and deletion. This can lead to a tree of the height of order n, and thus will have some nodes which are very deep inside a tree. The other approach to a balancing tree is a strict balance. This means that all the non-leaf nodes have exactly 2 children. Thus, such a tree will always be balanced perfectly. It will give an exact order log n time for search. However, the insertion and deletion will take a lot of time. Then the other will be a pretty good balanced binary search trees. These are the most common balanced binary search trees. These allow only a little out of balance. Thus, it does not allow the height to go to the order n, and hence keeps the search tree in an upper bound of log n, whereas also keeps insertion and deletion in the upper bound of log n, as you will see in the coming slides. Now, the fourth approach to a binary search tree is adjust on excess. These binary search trees are self-adjusting, that is, when we have to insert or delete node from these binary search trees, then it will automatically rearrange its nodes so as to give a height of the order of log n. Now, in this slide, we have shown that in the coming slides we are going to talk about AVL trees. We are going to give a basic introduction to AVL trees, and we are going to show how an AVL tree is just a little out of balance binary search tree and how it keeps its search, insertion and deletion operations in the order of logarithmic n. The AVL trees are good but not perfect balanced binary search trees. This means that the AVL trees allow a little bit out of balance. However, it does not allow the height to go to the order of n. The AVL trees are height-balanced binary search trees. This means that the invariant that will be applied to a tree to be considered to a AVL tree depends on the height of its subtrees. The balance factor of a node is given by height of the left subtree of a node minus height of the right subtree of the node. In an AVL tree, we will calculate these balance factors at every node. For every node, we will compare the height of the left and right subtree. The invariant that has to be maintained for a tree to be recognized as an AVL tree is that the height of the left and right subtree can differ by no more than 1. That is, our balance factor cannot be greater than 1. We will store all the current heights in each node so that we can compare the height of the left and right subtree and hence calculate the balance factor and thus make sure that it maintains the invariant that it satisfies the invariant to be considered as an AVL tree. Now in these slides and the slides to come, we will show that our height of an AVL tree will be of the order of log n. To show this, first we will have to define a quantity called nh, where nh is the minimum number of nodes in an AVL tree of height h. We will give this proof by induction. To prove this by induction, first we will have to define our base cases. We will define our base cases as n0 equal to 1 and n1 equal to 2. This means that an AVL tree of height 0 will have minimum number of nodes as 1. That is, an AVL tree of height 0 will have only the root node, whereas AVL tree of height 1 will have minimum 2 nodes, which comprises of one root node and one children of that root. Now, for like every other induction proof, we will define our induction step. The induction step will be given by nh, that is minimum number of nodes in an AVL tree of height h, is equal to the minimum number of nodes in an AVL tree of height h minus 1 plus minimum number of nodes in an AVL tree of height h minus 2 plus 1. Here, one thing that we have to consider is that we didn't consider the induction step as nh equal to 2 times nh minus 1 plus 1. This is because we are finding the minimum number of nodes, and the minimum number of nodes will come when when one of the subtrees is of height h minus 2. Moreover, we cannot take the height of any subtree as less than h minus 1 as less than h minus 2, because then the balance factor would be more than 1 and hence the invariant that needs to be satisfied to be considered as an AVL tree will no longer be satisfied. Now we will try to prove that the value of nh must be greater than or equal to phi h, where phi is a constant whose value is approximately 1.62. Now in this slide we are going to give a key idea of our proof. As I have already told about the induction step in the previous slide, that nh must be greater than or equal to nh minus 1 plus nh minus 2. Assume nh is equal to t raised by h. This is the assumption that we take in almost all the proofs in almost all of these kinds of proofs, where t is a constant. This will give us a quadratic that t square must be greater than or equal to t plus 1. When we will solve this quadratic, we will get a solution of the form of nh must be greater than or equal to a into t raised by h, where a is another constant whose value can be found using our base cases. Now, in this current slide, we have given an example of AVL trees. Here we see that all other nodes are AVL balanced, that is, the subtrees differ in height by at most 1. Now, we will continue our discussion for the height of an AVL tree. I have already said that nh must be greater than or equal to phi h. Suppose we have n nodes in an AVL tree of height h. Then n must be greater than or equal to capital NH, because NH is the minimum number of nodes in an AVL tree of height h. This implies that n must be greater than or equal to phi h, and hence log phi n must be greater than or equal to h. That is, our tree is relatively well balanced since log phi n forms an upper bound on the height of an AVL tree. We thus see that the height h must be less than or equal to 1.44 into log 2n. Now in this slide we are talking about node heights. We are talking about two trees, tree A and tree B. Both of these trees can be seen as an AVL tree as their balance factor has always less as the mod of their balance factor is always less than equal to 1. Now here we try to insert 7 into the tree B. We see that after inserting 7, the A tree B does not remain an AVL tree. The primary reason of this is that there has been an imbalance at node 9. It has one subtree of height 1 whereas the other subtree of height minus 1. This will lead to a balance factor of the value 2. However, for a tree to be an AVL tree, the balance factor cannot be greater than 1. Hence, an imbalance had occurred and the tree is no longer an AVL tree. Now in the next slide, the slides to follow, we will talk about insertion into an AVL trees. Now we are talking about insertion and rotation in AVL trees. As we have seen in the example given earlier, that insert operations may cause the balance factor to become 2 or minus 2 for some node. That is, they may cause imbalance at some node. We also observe that only nodes on the path from insertion point to root node have possibly changed in height. This is obvious. This is an obvious point. So after the insert, we go back up to the root node by node, updating the heights. Since we have said that the only change in height has occurred on the path from insertion point to root node, we only have to look about imbalances on this path. We see that if the new balance factor is 2 or minus 2, then we will adjust tree by rotation around the node. Rotation is something that we will talk about in the coming slides, and is the most important thing to discuss in AVL tree. Now, in the current slide, I have given an example of a single rotation in AVL tree. Here we see that the left child of node 9 has become its parent, whereas 9 has become a child of node 8. By doing this rotation, we see that the balance factor is satisfied everywhere, and hence our tree has again become an AVL tree. Now, in the current slide, we will discuss the various types of insertions that could happen in an AVL tree and the various cases that you will get when we try to insert a node in an AVL tree. Now, let the node that needs rebalancing be alpha. There are 4 cases. One is an outside case where we are inserting into the left subtree of left child of alpha. And the other is when we are inserting into the right subtree of right child of alpha. We will see that in both of these cases, our invariant for AVL tree can be satisfied by only a single rotation. Now, come the inside cases. These inside cases tend to be more complicated and usually require a double rotation. These inside cases can occur when we are trying to insert into the right subtree of left child of alpha, and the other can occur when we are trying to insert into the left subtree of right child of alpha. The rebalancing is performed through 4 separate rotation algorithms for these 4 different cases. Now, in this slide and the slides to come, I will talk about an outside case. Consider this valid AVL tree. Now, in this AVL tree, we have inserted a node into the subtree X. This has made the this has made a subtree X of height h plus 1 and node K of height h plus 2, whereas node Z is of height h. Hence, an imbalance had occurred at node J, and thus we need to perform a rotation to remove this imbalance. Now, an AVL rotation, an outside case. Here we will see that to maintain back the balance, we will have to do a right rotation. Here we will make node K as the here we may hope to make node K as the parent of node J, and the right subtree of node K to be the left subtree of node J. This is what you will see in the slide that follows. Now here we have done a single right rotation. Now here we are talking about a single right rotation. Here we are removing two connections. One is the connection between node J and K, and the other is the connection between node K and Y. We are also creating one new connection, that is between J and Y. And now here we have completed what we were doing in the previous slide by making another new connection between K and J. Now we will see that the node J has height h plus 1, and thus both the subtrees of node K are completely balanced. This is an example of a right rotation. We have seen that the balance factor for all the nodes have now been satisfied, and hence the AVL property has been restored. Now we are going to talk about a more complicated case in the AVL insertion. In the earlier slides, we talked about the outside case. In that slides, we only talked about right rotation. However, there also exists a symmetric left rotation. It is now left up to the viewer to read about the left rotation. However, in this slide and the slides to come, I am going to talk about a more complicated form of AVL insertion, which is the inside case of an AVL insertion. Here we have seen that we have inserted a node into the subtree Y. This has made the node K of height h plus 2 and node Z of height h. Hence an imbalance has occurred at node J. But will a right rotation solve this imbalance? Here we have done a right rotation. We see that a right rotation does not solve this imbalance. This is because node J has height h plus 2, whereas the subtree x has height h, and thus an imbalance still remains at node K. Thus we see that right rotation is not sufficient to solve this problem, and hence you will need a kind of double rotation to solve the problem. Now since this is a more complicated case, we will have to go deep into the subtree Y. We will assume that the root of subtree Y is node I. It has two subtrees V or W. Since node I has height h plus 1, we will node I has height h plus 1. We will make one of the V and W has to be of height h, and the other has to be of height h minus 1. One of the or both of them can be of height h or h minus 1. Now here we will do a double rotation. First we will do a left rotation from I to K, and then a right rotation from K to J. Now first is the result of the left rotation. This left rotation has made W of in this rotation we will have node K of height h plus 1, since node X and V can have maximum height h, whereas node W has maximum height h also. Thus I will have a height of h plus 2. Now we will see that after doing a right rotation, our whole tree will be balanced. This can be seen in the next slide. We will now do a right rotation between I and J. After the right rotation, we see that the node K can have a maximum will have a height of h plus 1, since the maximum of the height of subtrees x and v are h. Similarly, J will have a height of h plus 1, since the maximum of the height of subtrees z and w is h. This implies that both the subtrees of node I has the same height. Hence, after right rotation, the balance has been restored. Thus, in this way, we have solved the complex inside case by using double rotation. Now we are going to talk about implementation in an AVL trees. Here we will assume that an AVL tree will have a field to store the height, then we'll have a field to store the key, that is, it's the value of the node, and then there will be two pointers, one joining it to the left subtree and the other joining it to the right subtree. And as implementation, we could have improved the implementation by not storing the height but keeping the difference in the height, that is balance factor, which will be modified on the part of insertion even if we don't perform rotations. This will help This will help to reduce the amount of storage that we would be using. However, this analysis is quite complicated and hence we will be sticking to our analysis of height. Moreover, we can also see there's also an important fact written in this slide. It is written that once we have performed a rotation, single or double, we don't need to go back up the tree. This is because what we have seen in the previous slides also, that once we have performed a rotation, the height of the subtree in which the rotation has been performed does not increase. We hope that the viewer goes back in the YouTube video and re-listens to the entire examples, or maybe go to a tutorial to confirm the fact. Now, in the current slide, we are giving a pseudocode for single rotation. The pseudocode for single rotation is given as a single rotation from right. Here, we are doing a single rotation from right on a node n. Yeah, first we will make a new node p. Where we will declare a new node pointer p. We will assign p as the right child of n. Then we will make n's. Then we will make n's right child as x, and we will make n's right child as p's left child, where p is the node which has the subtree of y and z. Then we will make p's left child as node n, and then we will make the root node n equal to p. This will imply that p is now the root node having n as its children, whereas its subtree y is now the left subtree of node n, and hence in this case a rotation from right has occurred where p has replaced node n as the new root of the subtree. We also need to modify the height or balance factors of n and p after the rotation. Insertion in the AVL tree. Now we will see that whenever we need to insert an AVL tree, we will insert and leaf. As we have discussed before, that only nodes on the path from insertion point to root node could have possibly changed in height. So after the insert, we go back up to the root node by node, updating the heights wherever required. Now we will see that if a balance factor has become 2 or minus 2, this means that the invariant that needs to be satisfied to call a tree as an AVL tree has been broken, and thus we need to adjust tree by rotation around the node. Now in this slide and the slide to come, we will talk about insertion into an AVL tree. Here we are making a reference tree pointer t and x as the element. Here t is the root of the tree. We will see that if t is null, then we will just make t as a new tree. We will assign x as the key or data of t. We will make height of t as 0 since it is a new tree and does not have any children, and then we will simply return from this function. However, if this is not the case, then we will have to go deep down the tree. For doing this, there might be three cases. Case 1, where t.data will be equal to x. Here we are assuming that there is no duplication insert in an AVL tree. That is, once a node of a particular key has been inserted into an AVL tree, we will not get another request to insert a node of the same key into the AVL tree. The next is if t.data is greater than x. This implies that x will belong to the left subtree of t. Hence we have made insert t.left, x. We will then have to check if the balance factor got disturbed. We will see if height of t.left minus height of t.right equal to 2. This implies the balance factor has got disturbed. Then we will see if t.left data is greater than x, implies x is in the left subtree of t.left, and hence it is a classic case or outside case where we are inserting into the left child, where we are inserting into the left subtree of the left child, and hence we will do a simple outside case rotation from left. Else it is a case of else it is a more complicated inside case where we have to do a double rotation from left. Now we simply have mirrored the same ideas about insertion into the left subtree for inserting into the right subtree. This will happen when x is greater than t dot data. Then we will have to again check if the balance factor got disturbed. If height of t dot right minus height of t dot left equal to 2 implies that the balance factor has got disturbed. Here we will check if x is greater than t dot right dot data, that is if it is a case of inserting into the right subtree of right child of a node. Then it is a classic outside case and we will do t is equal to rotate from right t. Else we will have a complex inside case where we have to do a double rotation from right. Then we will do an end case. Then we will make t's height equal to maximum of height of t dot left or comma height of t dot right, and we will add 1 to it since it has a height due to its root node also. Then we will return from this function. Now in this slide and the slides to follow, I am going to give examples of insertions into an AVL tree. In the AVL tree that is given in the current slide, we will insert 5 and 40. We see that when we have inserted 5, no imbalance has occurred, and hence no need of rearrangement. However, similarly, when we insert 40, no imbalance has again occurred, and hence no rearrangement is required. Now we are planning to insert 45 into the AVL tree. We will see that when we insert 45, an imbalance occurs at 35 because it has its right subtree has height 1, whereas the left subtree has height -1, and hence it has balance factor of 2. Thus, we will do a classic outside case of right rotation to resatisfy the invariant for AVL tree. Now, in this slide, we are inserting 34 into the AVL tree. We see that the imbalance has occurred at node 30 because it has its left subtree of height 0 whereas right subtree of height 2. However, here the imbalance that has occurred is of the type of an inside case. Thus, it would require a more complex double rotation rearrangement so as to satisfy the invariant of AVL tree. Now here, I have given an example of double rotation. It is an example of double rotation from right. Here we will use the functions of rotate from left and rotate dot right that we have described before. Here we will first rotate from left ends. Here we will first rotate from left at taking n's right child as the root. This implies that we will rearrange that rearrangement will occur at the parent of node v and w and the parent of node z. Then we will rotate from right at the taking at the tree which has its root as n. That is, a rearrangement will occur between node n and the one which who is the parent of z. In the case, double rotation can be avoided to make the whole process efficient by not calling back both of these two functions, but making an implementation from the start. This this however will require us to let here this will disturb the modularity of the code, and this will make our code more difficult to understand. Hence, to keep our things as neat and simple, we have ignored the same, and we have just for double rotation we have called two rotation functions. Now, in the current slide, we are giving more examples of rotation. All these examples that we see in these the examples that we see in these slides are an examples of single rotation from the right. So, in the previous slide, we completed our discussion about insertion into the AVL trees. Now, in the current slide, we are seeing about deletion in an AVL trees. The deletion is much similar to the insertion trees, so we expect the user to go back and read about deletion itself. Hence, this discussion has been omitted. The main problem in deleting a node will come when the node will have two children. And then we will have to then when a node has two subtrees, then we will have to decide which node from among these subtrees is valid enough to take its place. As the user will see on reading about it through a documentation or tutorial, that the maximum element in the left subtree and the minimum element in the right subtree are the only two nodes that are eligible enough to take the place of the node in case of deletion of the node. However, we warn the user that whenever he is reading about deletion from any documentation, he must keep in mind that deletion, like insertion, will lead to imbalances, and hence a kind of rearrangement or rotation needs to be done so as to restore the invariant properties. Now, in this slide, we talk about the pros and cons of AVL trees. Now, we will talk about the main arguments for an AVL tree. The main arguments for AVL trees are that its search is logarithmic, since AVL trees always height balance, as we have proven earlier also that its height has an upper bound of log phi n. Moreover, insertion and deletions are also of the order of log n. Also, we see that height balancing has no more than a constant factor to the speed of insertion. Thus, all these are arguments for an AVL tree implies that it is very much time optimal and hence is a very good way of implementing binary search trees. Now, I'm going to discuss about the arguments against using binary AVL trees. First is that it is very difficult to program and debug. It will require a lot of space to it will require more space to store a balance factor. And if we are going to store heights, then it will require a lot of space of the order of log n. Moreover, although it is asymptotically faster, but rebalancing costs time. Thus, there may be a case that if n is small, it may not perform so good. Also, more large searches are done in database systems on disk, and they use other searches, for example, B trees. We request the user to go back and read about B trees and how it has various advantages over AVL trees. Also, we will when the user goes into depth to read about binary search tree, he will see that it may be okay to have order n for a single operation if total runtime for many consecutive operations are fast. This is a classic case of split trees, which have recently become very popular and are very commonly used. Yeah. This marks the end of my presentation. Thanks a lot for watching this presentation. I have tried to cover most of the AVL trees. However, if still you have any doubt, you can leave comments. You can leave comments below. So I'm going to just summarize whatever I have discussed. First, we have discussed about binary search trees. We have given an introduction to binary search trees, and we have seen why they are so widely used. Then we moved our discussion towards AVL trees, a special kind of binary search trees. We see how an AVL trees implementation has a very good time complexity. We have also proved how an AVL tree will have a height of at most log n, and hence ensures that the insertion, deletion, and search operations have at most takes at most log in time. Moreover, at the end, we also discussed that when we insert into the binary search tree, the invariant that defines when we insert into an AVL tree, the invariant that we have defined for AVL tree, that is the height of the left subtree and right subtree cannot differ by more than one, can get disturbed. Thus, so as to resatisfy the invariant, we will have to do some form of rotation so that the invariant holds and the tree continues to be an AVL tree. Then we give a brief discussion about deletion in an AVL tree and the pros and cons of an AVL tree. Thanks a lot for watching. Thanks a lot for watching. Please leave your questions in the comments below.